In this video, we solve problem 13.9.022 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to consider the following. We have 4 data points, x equals -3, y equals 0, x equals -2, y equals 2, x equals 2, y equals 2, and x equals 3, y equals 5. And we're asked to find the least squares regression line. And then we're also asked to find the sum of the squared errors. Now, the least squares regression line is just a line of best fit that sort of fits through these points. So we're sort of asking ourselves, okay, we know that these 4 points don't lie in a line, but we might have reason to believe that the relationship between the 2 variables represented by x and y is linear. I mean, it looks like they're kind of linear. I mean, there's obviously some error. There's a little bit of noise there, but you might say in general that these 2 variables have a linear relationship. And I'm just looking at this edge of my Post-it here. Might be looking for the line that sort of best fits through that data. And if you're saying best fit in what way, we're going to look for the line that will minimize what is called the sum of the squared errors. So let's write a couple of things down. When they ask you for the least squares regression line, they're just looking for a line. So f of x equals ax plus b. For sum a, that's a slope to be determined by us, and sum y-intercept b, also to be determined by us. And this is the line of best fit through this data. And we're going to choose a and b to minimize the sum of the squared errors. And that's why it's a Calc 3 problem. Now, in general, the sum of the squared errors is the sum as I goes from 1 through n. And that is assuming you have n data points. And those are typically denoted by x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3, all the way through x sub n, y sub n. So we want the sum of the squared errors. Now the error would be the difference between the y value on the line at a particular x value in our data set and the y value that actually goes with that x value in the data set. I know this is a little confusing to many students. You might think that this is a y value and that's a y value, so shouldn't it automatically be 0? It won't automatically be 0. This is the y value predicted by that line of best fit that we're trying to find. And this is the actual y value. For example, if we call this point x sub 1, y sub 1, the actual y value would be y sub 1 equals 0. If we call this point x sub 2, y sub 2, the actual y value would be y sub 2 equals 2. So this is a real y value, and this is a y value predicted by our model. We want to make the difference between the actual y value in our data set and the y value predicted by our model. We want that error to be as small as possible, but we can't just minimize the sum of the errors because they automatically cancel out. Because some of the errors are going to be, overestimates, or some of the errors are going to be positive, some of the errors are going to be negative. So some of the y values that we get from our model are going to be overestimates, some of them are going to be underestimates. We want to say any error is bad error, whether it's positive or negative. So rather than minimizing the sum of the errors, we minimize the sum of the squared errors. This is the sum as I goes from 1 to n of f of x sub I, which is just this function evaluated at x sub I, minus y sub I. N is known, x sub I and y sub I are known for I equals 1 through n. We'll call this one x1, y1. We'll call this point x2, y2. We'll call this point x3, y3. And we'll call this point over here x sub 4, y sub 4. So those are all known. The only unknowns in this equation are a and b. So when we minimize the sum of the squared errors, we're minimizing a function of two variables, which is why we need calculus 3 in order to minimize that sum. Now we could minimize this in general and come up with an expression for a and b in terms of x sub I and y sub I for I equals 1 through n. That's what they do in your book. Those are the formulas that you would see if you take a statistics class and you're just looking at the equations that give you the slope and y-intercept of that least squares regression line. And we could do that. But what I'd rather do, just to make the concept a little bit clearer, is I'd rather substitute in the x sub 1, y sub 1, x sub 2, y sub 2, the actual data that we have in this example. So let's do that. We've got x sub 1, y sub 1 is negative 3, 0. X sub 2, y sub 2 is negative 2, 2. I'm just reading this from the graph that was presented to us by WebAssign. And then I'm going to substitute these in. In our case, n is equal to 4. So we'll have a times x sub 1, so that's a times negative 3, plus b minus y sub 1, so that's 0 squared. And then we'll add a times x sub 2, so that'll be negative 2a, plus b minus y sub 2, which is 2 squared. And you keep going like this. I hope you recognize the pattern. I'm just substituting in my x sub I, and those are the negative 3, the negative 2, the 2, and the 3. Now, rather than multiplying on the right, I'm multiplying on the left. We had a negative 3, a negative 2, a 2, and a 3, all multiplying our a's. And then we had the plus b for all of those. And then we're also substituting in our y sub I. Those are the y values that go with those x values in our original data set. The y's were 0, 2, 2, and 5. We're substituting those over here. And we want to minimize this. We want to find the values of a and b that make this function as small as possible. I will rewrite my function now. Now you have some options. If you want, you could distribute for all of these guys. You could write this twice in FOIL. You could write this twice in distribute. I highly recommend using the chain rule though. It'll make your differentiation a little easier as long as you remember how to use the chain rule. Remember, if you're minimizing a function of two variables, you have to first find the critical points. And when you're finding the critical points, when you're working with a function of two variables, you're finding out where the gradient vector is equal to the 0 vector. So you'll compute the gradient, set that gradient equal to the 0 vector, and then you'll solve for a and b, points a, b. Those are the critical points. I'll call that a naught, b naught. Those are the critical points of your function. And that's an inside function, that's an inside function, that's an inside function, and that's an inside function. And so we'll be using the chain rule when we compute the necessary partial derivatives to come up with that gradient vector. So remember, the gradient of a function of two variables is that vector of first partial derivatives. We'll have the partial derivative of s with respect to a times I hat plus the partial derivative of s with respect to b times j hat. We're going to set that equal to the 0 vector. Now, a vector is equal, or two vectors are equal if and only if their components are equal. So the x component of this has to equal the x component of that. And at the same time, the y component of this has to equal the y component of that. This is a system of two equations and two unknowns. We want to solve for those locations A and B, or those values A and B that cause both of these equations to be satisfied at the same time. So first, let's compute the partial derivative of s with respect to A. Again, using the chain rule, I've got a function squared here. The derivative of a function squared is 2 times that function. That's the derivative of the outside, times the derivative of the inside with respect to A, treating B as a constant by the chain rule. So that's going to give us a -3 there. Then over here, we're going to do the same thing. We've got a function squared. We'll have 2 times the inside function times the derivative of the inside with respect to A, treating B as a constant. So we get -2. Over here, you've got 2 times the inside function again, plus the derivative of the inside with respect to A, treating B as a constant. Last one, we've got 2 times the inside function times the derivative of the inside with respect to A, treating B as a constant. And then it's just a lot of algebra. We've got -6 times -3A. That would be a +18A. -6 times B is -6B. -4 times the -2A is +8A. And we'll have -4B. -4 times -2 is +8. And we'll have 4 times 2A is 8A. 4 times B is the next term, and then 4 times -2 is -8. Then we'll have 6 times everything in these parentheses, so we'll have 18A plus 6B, and 6 times the -5 will give us a -30. Now we're looking for things to simplify. I've got a -4B and a 4B, and a -6B and a 6B. Okay, and let's look at our A's. We've got 18A, and 18A is 36A, plus 16A, that's going to be 52A. 8 minus 8 is 0, and then we'll subtract 30. And I think that's all the terms. We've covered everything. So that's the partial of s with respect to A, and that needs to be equal to 0. So we'll set 52A minus 30 equal to 0. And since it does only involve one unknown this time, we can immediately solve for A. We have 52A equals 30. So A equals 30 over 52, which you can write this way. That's 2 times 15 over 2 times 26. 2 is reduced, and you get 15 over 26. Those don't have any factors in common, so that is an A value at our critical point. Now we also need to compute the partial derivative of s with respect to B. Now one thing I want you to notice here is in the parentheses for all of these, B has a coefficient of 1 because we didn't multiply it by anything when we substituted in our x sub I and a y sub I. So for each of these guys, the derivative of each piece will just be 2 times the inside function for all of them. So I can write that down. So I have 2 times the inside function here. And then you just want to distribute. I think that looks good. And let's collect like terms now. The -4A and 4A reduce, -6A and 6A reduce. So the A's are gone. And we've got 2B and 2B and 2B and 2B, which is to be expected because there was a 1B in parentheses for all of these, and then we distributed the 2 in. So we've got 8B there. And then you've got a -4 minus 4 is -8. -8 minus 10 is -18. And I think that's it. I think we got all the terms. We'll set that equal to 0. happens to involve one unknown, so we can just immediately solve for b. We have 8b equals 18. Just divide both sides by 8. This is 2 times 9 over 2 times 4, or 9 over 4. Okay, now that is a critical point. We have not we have not discovered whether this critical point corresponds to a minimum or a maximum yet. I think you can probably tell that it's going to be a minimum just because of the form of that sum of squares. When you are adding a bunch of squares together, if you find an optimum value, it's going to be a minimum, not a maximum, because it's a sum of squared things. Like we can make this small, but it can go on to infinity. We could make the error as large as we wanted to. So I believe this corresponds to a minimum, but that's not enough justification. We really do need to confirm that the second partials test tells us that this corresponds to a minimum. So let's compute the Hessian matrix. This is the matrix of second partials. We take the partial of s with respect to a, and we take its derivative with respect to a and then b. Of course, those are all partial derivatives. And then we take the partial derivative of s with respect to b, and we take the derivatives with respect to a and then b. This is actually really simple because the partial derivative of s with respect to b is just this. It has no a's in it. So the derivative of this with respect to a is 0. The derivative with respect to b is 8. And then the partial derivative of s with respect to a was this 52a minus 30. The derivative of that, again, with respect to a is just 52. And there were no b's in this, so the derivative of this with respect to b is 0. Now, if we evaluate the determinant of the Hessian matrix at the critical point, that's going to tell us whether that critical point corresponds to a minimum value or a maximum value. Now, it just so happens that that Hessian does not depend on A or B at all. So this determinant is going to be the same all the time. And it's going to be 52 times 8 minus 0, which is clearly positive. Now, remember, if your determinant is positive, that tells you that you are either at a relative minimum or a relative maximum. And it tells you that the partial derivatives on this leading diagonal, the second partial derivative of s with respect to a and the second partial derivative of s with respect to b, those have the same sign. And we can just look at this and tell that they're both positive in this particular example. So if our determinant is positive, that means we're at a relative min or a relative max. To decide whether it's a relative min or a relative max, we look at these partial derivatives and we say, are they positive or are they negative? Well, they're both positive. Remember what that means. That means if we had a surface representing this sum of squared errors, if the second partial derivative of s with respect to a is positive, that surface would be concave up in the a direction. Remember, second derivatives give you concavity from calculus 1. And it's also concave up in the b direction. And if both of those happen at the same time, that means you're at a relative minimum. You're going to be at the bottom there. So that means S evaluated at AB, which in this case is 15 over 26, 9 over 4, is a relative minimum. And what does that mean for us? That means when we are trying to find our least squares regression line, we found it. It's f of x equals ax plus b, and we know what a is now, and we know what b is now. So a turns out to be 15 over 26. You can use y or you can use f of x. Either one is fine. Our slope is 15 over 26, and our y-intercept is 9 over 4. Now, if you're saying to yourself, okay, well, what is that exactly? You can use a calculator to approximate. I'm getting my calculator out. I tried to pause my video, but for some reason, on this new computer that I've been using, because my other computer is out of commission, not working nearly as well. It's not pausing when I want it to pause, so that's okay. It's take a little bit longer than usual, that's fine. This is approximately 0.577 times x. And of course, 4 or 9 divided by 4 is 2.25. Okay, so if we have a line with a slope of about 0.6 that goes through the y-axis at 2.25. So you'd go up 0.6 and then over 1. That is supposed to be our line of best fit through that data. Now, of course, this graph isn't the best. These tick marks aren't evenly spaced, but that's the idea. That's our 2.25, and our slope is that 15 over 26. We go up 15 when we run to the right 26 units. That's what that ratio would be. Obviously, we just went over 1 and went up, 15 over 26 units in that case. See how it does fit the data. I mean, we're a little bit below the line here, a little bit above the line here, a little bit above, or excuse me, the data is a little bit below the line and then above the line and then below the line and above the line. And then what we said was this was the line that would minimize the sum of the squared errors. Now the error is that distance from there to there, and that distance from there to there, and that distance from there to there, and that distance from there to there. So we just found the line. When they ask you now to find the sum of the squared errors, you can find the y values on the line and subtract the y values for each of your data points. That would give you your errors, and you could square them and add them together. That would give you S. You can also just substitute in your A and B values into this right here, and that will give you the same thing. So let's do that. S evaluated at 15 over 26 and 9 over 4 is, in our case, -3 times our A value plus B. This is the y value that is predicted by the line at x equals -3, minus the actual y value at x equals -3, which was 0. That was our x1 and our y1. And then we'll do the same thing here for the next point. X2 was -2, so we're going to take that -2, we're going to multiply it by the right slope. We're going to add that 9 over 4, and we'll subtract the y value that goes with that x equals -2. And this will give us our predicted y value on that line. And then this is the actual y value from our data, and we want to know what that error is. And you just continue like that. Oops, the next one was +2. X was equal to 2 when y was equal to +2. And then for the last one, when x is equal to 3, y was equal to 5. Now you don't have to do this to get the right answer. You could just, plug it in, see what you get. But I really like to think about the concepts. I like to see that this is the error between the y predicted by the line and the actual y value, or the y predicted by the line and the y value that we actually have in our data set. So that's an error, and that we're squaring it. So this is truly is, it's literally a sum of squared errors. So after I do the arithmetic, these are the y values predicted by my line. Let's find those errors now. Oops, that's for another assignment. I'm still trying to recycle all this paper. Guess I'm not recycling at the moment. I'm just reusing, but I like to do my part with all the paper I use. Okay, so for that first one, we had 27 over 52 minus 0. And that was approximately 0.519 squared. And then the next one, we had 57 over 52 minus 2. And that's approximately negative 9.03 squared. And then the next one was 177 over 52 minus 2. We got approximately 1.404 squared. And then the last one is 207 over 52 minus 5. And that is approximately negative 1.019 squared. Now, if we look at our scatter plot, hopefully that's consistent. This is the y value predicted by the line minus the y value in our data point. It's positive about 0.5. It looks about right. This doesn't look as right, but it's probably because my axis is not exactly right. Those tick marks are not exactly evenly spaced. But if I take this y value and subtract that y value, I'd expect a negative error there because we're taking the y value in the line, we're subtracting the y value for our data. This is positive and this one's positive. That's good. Since these guys are above the line, I would expect the error to be negative. Okay. So then if we add all of these guys together, that's going to give us the sum of the squared errors. Now, if we use these exact answers over here, and you're just going to substitute these guys into your calculator, let the calculator do the arithmetic for the most part, you're going to get 213 over 52. And 213 over 52 is approximately 4.096. That's approximately the sum of the squared errors. But WebAssign is going to want you to give the exact answer, 213 over 52. I hope that helps. Please let me know if you have any questions about that. I think this is a really great application of applied optimization.